we now want to start talking about magnets and magnetic fields. Right? And so many of us have probably seen something like this in either elementary or middle school, where a teacher brought in a bar magnet and sprinkled some iron fillings around it and noticed that the iron fillings follow these kinds of shapes around the magnet. And what the iron fillings are doing are just simply following the magnetic field lines of the magnet. And this leads to the conclusion that for a dipole, and a dipole is simply something with two poles, which a magnet has, right? One north and another south, so there's our two poles, that the field lines will form closed loops. Right? So that's our first rule for magnetic lines, magnetic field lines. Right? They must form closed loops. Right? And another property of magnets is that so far we have not seen a magnetic monopole. And what that means is it's not possible as of yet to separate a north pole from a south pole. If I take a simple bar magnet with north and south poles and I cut it down the middle, instead of getting a north magnet and a south magnet, what ends up happening is I get another south pole here and a north pole there. So we have not been able to separate the two poles away from each other. This is a little bit different from electrostatics, where remember we can have a positive charge or a negative charge, and these are what are called monopoles, and the field lines in this case emanate directly outward instead of forming closed loops. Right? So this is one fundamental difference between magnets and charges, right? But they are similar. And in one way that they are similar is that if I have a bar magnet here and a bar magnet here, and let's say this is a north pole and then the south pole would be over in that direction, and this is the south pole and the north pole would be over off in that direction, and I know what the distance between these two magnets is, then I can measure the force. And it turns out that the force is similar to Coulomb's law. And it's similar in that they're both inverse squares. Right, inverse squares. So what that means is that the force is proportional to 1 over the square of the distance between them. And that's just the same thing that we saw in Coulomb's law. The actual form of the force law is a bit more complex, so we will leave that alone for now. But just understand that this does have the same form mathematically that Coulomb's law also has. Right? Okay, so where do we find magnetic fields? Do we only find them around magnets? Right? Do we only find them in magnets? And the answer is no, right? We've already seen that we can have field lines kind of forming these closed loops for a bar magnet, And the same would be true for like a circular ceramic magnet or something of that nature. But we also find them in wires with current in them. And you can prove this by hooking up a circuit, and let's just hook up a small circuit here. So here's my battery, and I'll let my wires be long, and I'll just put a small resistor in there to modulate the current just a little bit, and especially if R is small, then the current will be larger and the effect is magnified. So let's say I have some current I running in this direction, and I have a compass needle that's not necessarily oriented north-south with the wire. The needle will still deflect directly toward the wire. Right? The needle will still deflect directly toward or away from the wire, depending on the wire's orientation. And what happens is, as the current is running through the wire, magnetic fields start to kind of wrap around the wire in concentric circles. And it'll do this in both sections of the wire. And if we have this particular configuration, the wires will exert forces on each other because of their magnetic interactions. So these wires will put forces on each other. All right, and let's look at this in just a little bit more detail. Okay, so in what direction are the magnetic fields oriented? We said that they're concentric circles around the wire. They kind of wrap themselves around the wire. And let's look at how they do so. So let's just say that I have one wire with some current running through it in the upward direction. Where and how is the magnetic field oriented? So the magnetic field will wrap itself around the wire in concentric circles, and the direction that the magnetic field will have is indicated by the right hand rule, which says point your thumb in the direction of the current and then wrap your fingers around the wire. And that, where your fingers, the direction your fingers are pointing, will be the direction that the magnetic field is pointing. So if you do that, if you point your right thumb in the direction of the current and start to wrap your fingers around the wire, you'll discover that the magnetic field is going into the screen on this side of the wire, and it's coming out of the screen on this side of the wire. Okay? And that has some very interesting implications. Let's go back and visit the two-wire scene here. So here I have two parallel wires, and let me make this guy just a little straighter. We can draw a better line than that. Okay, so I have two parallel wires, and here we have some current running in this direction, and over here we have some current running in the same direction. And again, these will be separated by some distance r. Okay? Now, in this case, will the force be attractive or repulsive? Right? Will these wires attract each other, or will they repel each other? Right? And let's answer that question. So we know the magnetic fields are going to wrap themselves around like this, and they'll wrap themselves around like this, and use the right hand rule to find the direction that the fields will be pointing. So again, here they'll be pointing into the screen, here they'll be coming out of the screen, here they'll be pointing into the screen, and here they'll be coming out of the screen. Ooh, okay. So in the middle, what we effectively have are two opposite poles. You can think of this as a North Pole and a South Pole. It's not exactly a North Pole and a South Pole, but you can think of these magnetic fields representing opposite directions or opposite poles. So here we have a direction out of the screen, and here we have a direction into the screen, and opposites attract. So in this case, the wires will be attractive. Okay, so the wires will actually kind of bend inward just a little bit toward each other, like so, and you can actually see this deflection in the lab. Right? And how would we get the wires to repel? Well, we would just need two wires and run current in one direction and run current in an opposite direction, and these wires would kind of bend outward after the current had been running through them just a little bit. Okay? So that's how you would get the wires to repel. Alright, so now that we kind of have a sense how we can kind of create some magnetic fields other than some magnets, if a magnetic field affects wires, or if current can generate magnetic fields, do magnetic fields also affect individual charges, right? So the question is, do magnetic fields affect charges? And the answer turns out to be yes and no. Okay? So yes, if the charge is moving. No, if stationary. And there is a slight caveat in the moving. The motion cannot be parallel. With the field, right? So the motion can't be parallel with the field. Oop. Okay. It must be at least in some way not parallel with the field. It doesn't have to be completely perpendicular, but it must be not completely parallel with the field. All right. And so let's see how this works. Let's imagine that I have a giant bar magnet, right? Well, maybe even a giant horseshoe magnet might work better. So here's one pole of the horseshoe magnet, and it wraps around beyond the screen, and then the other pole of the magnet is down here, and let's say that this is the North Pole, and that this is the South Pole. And the way that magnetic fields work is that they start on the North Pole and terminate on the South Pole, so my magnetic fields will look something like this. And again, the further away from the edges you get, you will get the nice bowing effect. But again, we will not be too concerned about that. And I want to know, let's say I have some positively charged particle, and I want to shoot it through this magnetic field, and I want to know what it's going to do. How is it going to be deflected? Is the magnetic field going to put a force on it? And I just alluded to the answer of that being yes, and so the particle will run through the magnetic field and it will be deflected. Right, it'll be deflected. But in which direction? So again, we have a second form of the right-hand rule, right? And what this says is point your thumb pardon me, not your thumb, but your forefinger, point index finger, in the direction of motion, point your middle finger in direction of the field, and your thumb will point in the direction of the force. And so, if we apply that logic to this picture here, this will be our index finger. This will be our middle finger. And if we do this, so our index finger points to the right, our middle finger points down, and our thumb points away from us. So this particle, once it enters the field, will get deflected into the screen. All right, it'll experience a deflection into the screen. And if it were a negatively charged particle, it would experience the opposite. So the right-hand rule is defined for positive charge. So let's write that down. So the right-hand rule is for positive charge. And it works the opposite way for negative charge. So the best way to figure out how a negative charge will be deflected is to find out the direction of positive charge with the right-hand rule, and then just simply reverse that direction. So if it's into the screen for a negative particle, it'll be out of the screen. If the positive particle is deflected upward, the negative particle will be deflected downward, and so on and so forth. All right. So how is that force actually described? Okay. So mathematically, the force on a particle will be equal to QVB. All right. So now we've introduced this letter B, and this is the magnetic field strength. All right, so that's the magnetic field. And we measure the magnetic field in units of Teslas. And by definition, 1 Tesla, right, is equal to 1 Newton per 1 amp times a meter. All right, these are a little bit of funny units. We have units of force over units of current times a unit of distance. All right, but this is how the magnetic field is defined. All right, and so this is the equation of a charged particle in an external magnetic field B. All right, and V is the velocity of the particle, and Q would be the charge. Okay. Now, what if we have the same situation? Let's remake our bar magnet here, right? And we have our magnetic field in the middle here, pointing from north to south. And what if instead of having a individual charge run through here, what if I had a current carrying wire, right? How would this be deflected? And so imagine that I have some current running through here, I. And if we suppose, somewhat incorrectly, that our current is made up of positively charged particles, once the particles enter this magnetic field, right? Once our particles enter the magnetic field, they will feel the effect just like a single particle would. And so the net effect would cause a deflection. In this case, how? Right? How would it cause a deflection? Well, before we said that this would be into the screen, and that's the effect that we would see here. The wire would be bent into the screen. Okay, so the wire would bend into the screen. And like before, there's a nice little formula. Instead of F equals QVB, the formula for a wire being in an external magnetic field is just I, which is the current, L, which is the length of the wire, and the strength of the magnetic field B. So if I know the strength of the magnetic field, I know the length of the wire, and I know the current in the wire, I can deduce the force that would be exerted on the wire. Right? And let's do one more. Let's revisit the parallel wire case. Okay? So we said that these will exert a force on each other if I know the distance between them r, and they're carrying some current. Alright, so how do I actually describe the force between these two wires? Now we said when the currents are the same, they'll attract, so the wires will bend inward just a little bit. Right? So the wires are going to bend inward, but how do we actually describe that force? Okay, so instead of describing it just as in terms of a pure force, it makes sense to determine the force in terms of the force per unit length of the wires. Alright, and this allows us to neglect how long the wires are. We don't have to worry about how long the wires are if we just calculate the force per unit length. Alright, and so the way to do it is we'll call this I1, this will be I2, and the force per unit length on two current carrying wires is going to be 2 times a new constant K prime I1 over I2 divided by R. So instead of going as the square of the distance between them, current carrying wires, the force only goes as 1 over R instead of 1 over R squared. Alright, so now let's look at some examples on how to apply all three of these formulas. Okay, so let's look at an example where we have a particle traveling in a uniform magnetic field where the motion and the magnetic field are perpendicular to each other. Okay? So let's look at an example, and here we have a charge, and let's say he has 0.4 coulombs. All right? And the magnetic field strength is 0.5 Tesla. And let's say we measure the deflection once the particle is in the magnetic field, and we measure the particle's deflection, and we can measure the force, and the force is found to be 100 newtons. Okay? Under these circumstances, what is the velocity of the particle? Okay, that's the question we're going to ask. So how do we set this up? We start with F equals QVB, and now I need to solve for V. Right? So I want to solve for V. In doing so, right, I just divide both sides by Q and by B. And the result is V is equal to F divided by QB, which is going to be 100 newtons divided by 0.4 coulombs times 0.5 coulombs, and this turns out to give us, when you punch that in all into your calculator, 500 meters per second. Oh, this isn't coulombs. Sorry, this is in Teslas. Whoops. Yeah. Right, so that's Teslas. And the result is 500 meters per second, which seems pretty fast, and it is, but not terribly fast for individual particles, right? Small subatomic particles. That's actually rather a slow speed. So that's not out of the realm of possibility, right? But that's how you would use the equation, and that's one example of how to manipulate it. So let's look at a second example, and let's say that I have a wire, and it's in an external magnetic field. Right? And the wire has a current of 3 amps. The magnetic field strength is 0.6 Tesla, and the length of the wire is 20 centimeters. And we want to calculate the force that's on this wire due to the external magnetic field. Right? So again, let's just plug it into F equals I LB, where I is the current, so this is going to be 0.3 amps. Oh, I'm sorry, it's 3 amps. It's 3 amps. L is 20 centimeters, which is 0.2 meters. And our field strength is 0.6 Tesla. And when you plug this into your calculator, this will give you 0.6 amps times meters, and 0.6 times 0.6 is 0.36, and the units here are in newtons. Alright, so that's how you would find the deflection of a current carrying wire in an external magnetic field. Alright, our final example, let's look at 2 wires, a distance of 15 centimeters apart, right? And both wires are carrying a current of 1 amp, right? So here we have I1 equals 1 amp, and here we have I2, and let's let it be in the same direction, and that'll be 1 amp, right? And we want to find the force per unit length between these 2 wires. And remember, since the currents are going to be in the same direction, these are going to be attractive. Right? And so let's actually do the calculation. Let's plug all this in. So remember that F, force per unit length, F over L, is equal to 2, and that funny constant K prime is equal to 1 times 10 to the negative 7th newtons per square amps. Alright, that's the units on that funny constant K prime, which it serves the same purpose as Coulomb's constant does, but it's not the same as Coulomb's constant. And so I1 was 1 amp, and I2 was 1 amp, and the distance between them was 15 centimeters, or 0.15 meters. And when we plug all this into our calculator, we get a final force per unit length of 1.33 times 10 to the negative 6th newtons per meter. Alright, which is a unit of force and a unit of length. And again, if wires are, if the currents are parallel, so if I's are in same direction, then the force will be attractive. And if they're opposite, the force will be repulsive. But the magnitude will not change. This magnitude will not change. Alright, it will only change how the wires affect each other. Well, they will bend inward toward each other or away from each other. Alright, so there's a brief introduction to magnets and how to use some calculations. And the next video will focus on the second half of the chapter. We will see you then.